Um, all right. That didn't sound like David, but I suspect he triggered.
It was a little robot. We haven't experienced that before, but here we go.
Okay, so this is your chance to leave if you wanted. Okay. Um, Tim, you can take the screen.
All right. Let's see here. Okay. All righty. I hope that everyone can hear okay. If not, well, if not, you wouldn't have any way of knowing, would you? Let me know if you can't hear me, and let me know if you can't see what's going on here. So anyway, Ken had asked me to, I had done that Longitude for Beginners program some time back, and Ken had asked me to do something about how longitude and latitude are determined today. So I agreed to do that. So here we go. I always like to look at this statement. To get where you want to go, you have to know where you are. You've got to know your starting point. And the other is to know where you are, you have to know what time it is. It is very interesting to me that this is the case. So I want to start off with a thought experiment. This is one of those kinds of things that I like to do because I think it helps explain a lot of the things we're going to look at. So when we were children, we learned that when we saw a lightning flash, we would immediately then begin counting. And we would count until we heard the thunderclap, and we knew that the time multiplied by the speed of sound would give us the distance between where we were and the lightning strike. So I just picked a random little section of a map of Denver and said, okay, let's assume that we've seen the lightning and listened for the strike. And I have counted X number of seconds and know the distance between the lightning and me. But because I'm sitting inside a house with the blinds drawn and all that kind of thing, I have no idea where that lightning actually hit. All I know is that it hit someplace on this red circle. But I can't tell you exactly where that is. So what to do about it if I want to know the exact location? Well, one thing I might do is I might ask for your help. And we get on the telephone, and you and I are on the phone, and we watch for the next strike and immediately begin counting. And you count and I count, and we draw circles just like they do in all the cops and robbers movies. You know, there's always drawing a circle around something. And if we have a situation where the two circles touch, they're tangent to each other on the inside, we know that that has to be the place where the lightning struck. And the other thing that can happen is if maybe we're a little bit farther apart, we have a situation where our two circles touch, but they touch on the outside rather than from the inside. But again, because we know the distance between ourselves and the strike because of the time, we know because of the two of us collaborating, we know that this is the place where the strike took place. Now, those two things are kind of unusual and unique situations. Generally speaking, we hardly ever get that lucky to have the strike be in tangent to the circles. More often than not, what happens is we get something like this. The two circles overlap. And now what do we know? Well, what we know is that we've got two spots where the lightning could have struck, but we don't know which one is the right one. So the next time we try this little experiment, what we do is we enlist a friend of ours, and all three of us get on a phone in a conference call, and we wait until we see the flash and start counting. And then all three of us report our times and we draw our circles, and we see that the three circles overlap in a single point. And now we know where that lightning strike took place. And the process of using 3 points like this is referred to as triangulation. And you know, it's a time-honored system for finding things. Interestingly enough, I was in a thrift store, and I found this device, which I thought was really clever. But this is called an outers locator. And inside the box is a device with a sort of a circular protractor on it and some arms. And the concept is, what you do is you sit in the boat and you've just found this wonderful fishing spot where the fish are biting like crazy. And you get out your outers locator and you point the three legs at three different landmarks that you can see. And then when you do that, you write down the numbers that you see on the circular protractor. The O points directly at, say, in this case, the boat dock, and the A points to the high point, and the B points to a tree. And you write down the numbers. The O is always 0, and you write down those numbers, and then the next day,
Oh, Tim, you have frozen.
It's dead.
Oh, technology, ain't it wonderful? Let's see. And Tim evidently logged off. Hopefully he'll be back in a second. If Zoom were made by Microsoft, they would say, turn it off and wait 5 seconds and turn it back on.
Maybe it was a lightning strike.
Yes, now we know how far it is to the lightning strike. Has anyone seen one of those locators in person? No? Tim finds the most wonderful things at his, there he is.
Okay, I'm back. I don't know what that was about. I don't know whether that was me or somebody else or what in the world. So let's try again to pick up from where we left off, I guess.
Good.
So let's see here. Okay, so okay, this is where I left off visually. So anyway, what I was saying when I was so rudely interrupted was that you have a little point in the middle of this thing and little notches at the ends of the arms so that you can sight the various landmarks that you've chosen. And then, as I say, once you've got the thing set up to where you had it, you can then find your way back out until the points all line up and you have arrived at the same spot you were in the previous day where the fishing was so good. And this is the kind of thing that, you know, you can do with this. I think it's pretty obvious. You see why we call it triangulation, because there are triangles involved in the process. And it's one of those things that is easier in theory than it is in practice, but that's how that works. Triangulation was also used by the Luftwaffe in the Second World War as part of their Battle of Britain strategy. In that case, what they did was they actually set up multiple radio beacons, generally speaking, 2 of them converging at the target point. And the idea was that the planes would fly out and try to stay on the beam as best they could. They had it set up with their radios so that if they deviated, say, to the north or to the right or to the left, they would get a change in the signal. But the idea was that then they would figure out how long they'd been flying and what their airspeed was. And when they figured that out, they knew whether or not they were over the target. If there was no visual identification possible because of either blackout on the ground or weather problems, you just let your bombs go and hoped for success. And sometimes it worked and sometimes it didn't. But again, a sort of a triangulation process. Well, that all works just dandy when we're talking about a flat surface like a map or, you know, a short distance excursion. But the truth is, the Earth is pretty big and about 8,000 miles in diameter. And it is an oblate spheroid. It's not at all flat. So it's a problem to do this over any considerable distance. As we know, you know, when ships sail away from us on the ocean, they look like they're sinking. And that's because they're actually going down the curvature of the Earth, and we can't see them at all at an eventual point. This is also why ships for all eternity had things like crow's nests where a lookout could be up high and thereby see farther than anybody on the deck, and able to pick out items that were a distance away. Best case, on a good day, you might be able to make a maximum of about 16 miles from the ship using that kind of observation. Now, you might ask the question, though, how do we know that the Earth is spherical? And the fact of the matter is there's a lot of confusion about this subject. But there are a whole bunch of reasons why we know that the Earth is spherical and that the flat earthers are just plain flat wrong. For one thing, when we have a solar eclipse, we know that the moon passes in between the Earth and the sun, and we can quite clearly see the shape of the moon impinging upon the sun. So we know that the moon is almost certainly more or less spherical. The same thing happens when we have a lunar eclipse where the Earth comes in between the sun and the moon, and the shadow of the Earth on the moon is also circular. So that's how we know that certainly it is circular. And then in 200 BC, Eratosthenes knew about a well in a town called Syene, which is modern day Aswan. And this well, at one time every year on the equinox at noon, the sunlight would shine all the way down to the bottom of this very deep well and not touch the sides of the well at all. Now, again, we have to remember how we know when it's noon. Noon is not when the sun is directly overhead. Noon is when the sun is at its highest point. Noon is when the shadows of objects are shortest. So they knew about this well in Syene, and they said, well, let's see what happens in Alexandria, which is about 600 miles away, on that same day at noon when the shadows are at their shortest. And they found that, yes, indeed, the shadows were short, but they were not non-existent as they were at Syene. And so he was able to use some very elementary geometry to determine that the angle of the shadow at Alexandria indicated the same angle through the surface of through the Earth to its center, and was able to determine from that the actual circumference of the Earth. And according to a lot of authorities, 200 BC, Eratosthenes did a pretty damn good job of actually measuring the circumference of the Earth, given what was known in those days. So as of 200 BC, for sure, we knew that the Earth was a sphere. Later on, Ptolemy decided to lay out a grid on the surface of the Earth, and he created the concept of latitude and longitude. And that was about 300 years later, but it was in the early part of the CE. So this became a very common practice, and so much so that by 1482, when this map was made, it was very common to use latitude and longitude lines. And I point out that this is 1482, 10 years before Columbus. So people who tell you that scientists believed that the Earth was flat, that Columbus didn't know that the Earth was a sphere, and so on, generally speaking, they're just plain wrong. Anybody with an ounce of sense and with a modicum of scientific knowledge knew that the Earth was a sphere long before Columbus's voyage. So we still had to figure out where we were. And in those days, we didn't have any way of measuring longitude. So we used a technique which was called dead reckoning. And dead reckoning consisted of doing things like measuring the speed of the boat through the water. And you did this by dropping this wooden device over here, sort of like a pie wedge, into the water. It was weighted, and then you let the line go off the reel and timed it for a period of 30 seconds. So you had to use time to figure out how fast you were going. You counted the number of knots that were passing through your hands as you did this, and then you did some calculations, and this told you your speed through the water. But you had to do all kinds of things to figure out where you were. You know, you had to make allowances for your compass bearing. You had to make allowances for the wind, for drift, for all kinds of things. And at best, it was a very, very approximate process. In fact, that's part of the reason why explorers who left Europe and headed for the Indies tended to hug the coast of Africa because they were much more comfortable if they could keep land in sight at all times. They weren't afraid of sailing off the edge of the earth. What they were afraid of is that they were going to go out on the open sea and get completely lost. So I like one thing about this that I point out to you is the fact that you've got a bucket over here underneath the cord reel, because you could imagine that that line coming in from the ocean after a test was probably pretty wet, and this kept you from making a mess. So as time went on, one of the things that was finally determined by the time of the 18th century was that if we could figure out what time it was someplace, say London, and Greenwich to be more specific, we could then figure out from astronomical observations what time it was wherever it was that we were on the ocean. And we could then calculate the amount of time difference between the two and calculate our longitude. And that was, of course, the great triumph of John Harrison to make a chronometer that was adequate to the task. And that kind of system, frankly, worked very, very well. It worked so well that we continued to use it for a couple hundred years, all the way down to World War II. And so you see there a Hamilton chronometer in Model 21, typical of the type used by the United States Navy during that time. But along about 1945, something happened. And that was this. It was the atomic bomb. You know, we now had the capability of destroying the world. It was that simple. We now had the ability to blow everybody up and destroy civilization as we know it. So what we did, because we were afraid of the Soviets, is we buried missiles, intercontinental ballistic missiles, underground. And the idea was that what we would do is we would hide them there and then, if need be, send them around the world to destroy our enemies. Trouble was that everybody was using things like this, like the U-2 spy plane that we had, to fly around the world and take pictures. And it didn't take very long for us and the Soviets and everybody else to be able to figure out where it was that everybody's missiles were, or at least a lot of them. So that wasn't working very well. The other thing that was happening was that we were creating maps using this aerial photography of all these missile sites. And we were creating a situation that we ended up calling mutual assured destruction, which said that none of us were going to send our missiles against each other, because we knew that if we did, the other guy would send his against us, and the result would be a total global conflagration. And that would be assure the destruction of everybody. Because of the difficulty of hiding these things, we did things like put them on B-52 bombers and have them fly all over the place, so that it was very difficult for our opponents to keep track of them. And we also put them in submarines so that they could be sailed anywhere on the planet and fired from there. These kinds of things required us to come up with better navigation aids. And again, it emphasizes the point: to get where you want to go, you have to know where you are. And so we developed a variety of different things, sometimes called things like C-Core, and this one was called LORAN. And LORAN actually stands for Long Range Navigation. and it was a radio system. And the thing was cumbersome, heavy, slow, and you had to have transmitters on land and on floating buoys, and was very difficult to provide a reliable system with that kind of arrangement. And the other thing was it was impossible to cover the entire Earth. Couldn't be done. So once again, another landmark event occurred, and that's this, Sputnik, 1957. The Soviet Union launched the world's first satellite into space orbit. And the interesting thing about that for our story is that there were some scientists here in the United States who were monitoring the radio signal from Sputnik. And they realized that the signal changed its frequency, its tone, not its radio frequency, but its sound. And it was higher when it was approaching them, and it was lower when it was going away from them. And turns out that they were able to figure this out, that this was the Doppler effect. It's like when a train, when a train passes you on the platform, the sound goes higher in pitch as it approaches, and it goes lower in pitch as it goes away. And the flash of insight that these guys had was they said, well, we can use this change in pitch to tell us whether Sputnik is approaching us or has gone past us. Now, we could also turn that around. If we knew where Sputnik was, we could use that Doppler shift to tell us where we are. If we knew exactly the position of the satellite, we could use the Doppler shift to tell us where on Earth we were sitting, especially if we happened to be out at sea. So the insight there was what led to what we now call the Global Positioning System, or GPS. We now have a setup where we have approximately 24 satellites flying around the Earth, orbiting the Earth at all times. You'll see different numbers, and it's because the number of satellites changes. I've seen numbers as high as 27, but we also have spares. We have half a dozen spares out there, so that if one of these things has a malfunction or a problem, we can switch another one into use. These satellites tell us a lot about navigation. So each one of the satellites on a regular basis broadcasts a signal that contains its name, the exact time of the broadcast, and its position. So you got this kind of thing from 24 satellites happening all the time. And those signals then, of course, are received by GPS receivers. So if we know the time that the signal was sent, and we know the time that we have at our location, then we know how long the signal took to get to us. And it's the same thing as we did with the lightning. We multiply the time in between transmission and reception by, this case, the speed of light, more or less. And I'll tell you why more or less later. And we then know the distance between the satellite and our GPS receiver. The satellites are arranged so that we have a different number of satellites in view at all times. But as we'll see, we need at least 4 to do a good job. And the more we have, the better the job we do. So as you can see, it's shifting here, but 6, 7, 8, 10 satellites may be in view from a single spot at any given time. So just as we did with the lightning strike thing, we had 2 circles. The 2 circles overlapped, and we had 2 points of intersection. Well, the problem is we're not dealing with a flat plane. We're not dealing with a flat map. We're now dealing with essentially the Earth and its curvature and satellite transmissions, which are out 12,000 miles from the surface of the Earth. So we're dealing with spheres and no longer just circles. And when two spheres intersect, you get a circle. That's what the intersection of two spheres is. If you think about it in terms of if you took two balloons or two beach balls and squashed them together, the intersection of the two of them would be a circle. Well, that's not very helpful because a circle has an infinite number of points. So we're almost back at the situation where when we were just all by ourselves trying to determine where the lightning strike was. So what happens if we add another sphere? Well, when we add another sphere, we now have three spheres intersecting, and the intersection of our circle that we started with and the third sphere, now we've got 2 points again, much like we had when we were doing the lightning thing. So how can we get to 1 point? Well, we get to 1 point by getting 4 satellites in view at the same time. And that results in an intersection that is a single point. So we have to have a little bit more data than we used to have when we were just doing the flat piece of work. So when we do this, we refer to this no longer as triangulation, but trilateration. And the first thing that it does is it gives us latitude and longitude, but it also gives us altitude, which is helpful because then it can be used.
Oh, no.
Gee. Need to have a GPS to find him.
For aviation and things of that sort. Yep, we dropped again. I don't know what's happening here, folks, but we dropped again. So let me bring it back to where we were when we were interrupted the last time.
The Air Force, the Space Force may be monitoring your transmission.
Yeah, that could be. That could be. So let's see here. All right, let me see. Let's see. I got to get to this, share screen, bang, bang. Okay, now we're back. So as I said, we're about 50 feet, 15 meters or so or less with 4 satellites. And as I said, if we go up to more and more and more satellites, things get better. But 50 feet is awfully good when you think about it. Back in John Harrison's day, they hoped to get within sighting distance, you know. So 50 feet is pretty damn good for navigational accuracy. So it was so good, in fact, that before 1983, the United States deliberately downgraded the accuracy of GPS for military reasons. In other words, we didn't want other people or spies or anybody to be able to get into this system and figure out where stuff was that we didn't want them to know. And so we actually degraded the accuracy of the system to prevent that from happening. And of course, not everybody had GPS. However, things changed again. And that was in 1983. And in 1983, Korea Airlines Flight 007 was traveling from Anchorage to Seoul. And they drifted off course. And they passed over Soviet territory, the Kamchatka Peninsula. And the Soviets scrambled fighters and shot the plane down, bringing it down just after it passed over Sakhalin Island. 269 passengers and crew died as a result. So Ronald Reagan, then president, said, okay, we're going to make GPS available for everybody because we're not going to have the tool to prevent a tragedy of this sort and not share it with the world. So that is exactly what we did. The accuracy of GPS at this point, the very best, with multiple satellites and so on, is on the order of plus or minus a foot. That's quite extraordinary, quite frankly. And it resulted also in our competitors deciding to create their own systems. After all, they said, well, you used to degrade the signal, you could do it again. And so they didn't want to be reliant on our system for their navigation. So Russia came up with a system they called GLONASS. China, Baidu 2. Europe has a system called Galileo. India, NAWCC, and Japan, QZSS. So we have all these competing systems. The last two, India and Japan, those are geostationary satellites. They do not travel around the way ours do because they're really trying to confine themselves to their own area of interest. But we have lots and lots of competitors for the GPS system nowadays. As far as reliability is concerned, like everything else, you know, we know that it was difficult in the days of sextants for people to take readings when the weather was bad. So there are limitations for us as well. How many satellites are visible? If they're not at least 4, you're not going to get a good result. Signal strength and noise, it's radio after all. Multipath effects. The signals bounce off things like mountains, and in cities, they may bounce off buildings, and you may have a great deal of difficulty getting good GPS in a big city. There are also what are called ephemeris errors, which have to do with variations in the orbital path of the satellite itself, even though it's tracked constantly by ground stations and the path is well known, there still are variations. The atomic clock accuracy is a small factor. If the atomic clock drifts, there'll be a problem. Two of the most interesting, though, I think, are Einstein. I'll mention that in a moment. Receiver clock accuracy, of course, is if we had the ability to receive the signal using an atomic clock, then things would be great. But after all, an atomic clock probably costs on the order of minimum 50 grand. So we're not going to have an atomic clock in our cell phones. It isn't happening. And as I said, Einstein gets involved, the theory of relativity. Special relativity says that the clock slows down at high speeds. As the speed increases, the clock slows down. So it turns out that the clocks in the satellites lose about 7 microseconds per day. And then general relativity says that the clock speeds up because of the reduced gravity that the clock experiences at its 12,000 mile orbiting altitude. And that causes the clock to speed up by about 45 microseconds a day, with a net being about 38 microseconds a day of difference from correct time. And unfortunately, what that amounts to is about 7 miles a day. So if we did nothing at all, our atomic clocks and our GPS system would be varying by 7 miles a day just as a result of these factors. So there are, as we nowadays say, there are hacks, things that are done to fix all this crap, you know. For cell phones, for example, like most of us have, we have something called assisted GPS. We know very, very well where the cell tower locations are with a great deal of accuracy. And so we can use the cell tower locations to help us get more accurate readings. We can also discard obvious errors. You know, if you get a calculation that says that one of your points is 15 miles above the surface of the earth, and you're driving in your car, you know good and right well that that one is not of any value, and you can throw it out. So we discard obvious errors. There is mathematical way of using the earth itself as one of your 4 spheres to get your minimum. And there's a situation wherein our cell phones are, in fact, as I said, not all that accurate. They usually use just quartz clocks inside them. And so they're not producing a very accurate time for the arrival. So what we do is we use the cell towers to transmit corrections to us on a regular basis, and then the cell phone is able to monkey with the internal time and correct it. The other thing that happens is because of this, the cell phone is getting its time correction on a continual basis. That is, every little bit of time, it gets a little bit of a tweak. And we can actually, if we want to, use things like artificial intelligence to try to figure out a way of applying a correction to it. The net result is that we end up being able to have something on our cell phones. This is an iPhone screen, but on the left, you see there's an extra app, and the extra app contains a compass function. And when you go to the compass function, you see that it tells you your bearing, and it also tells you your latitude and longitude down to the second. Now, the second of longitude, for example, is about 15 feet, roughly. 1 second. So if that, went to 105, 16, 16, it'd be a variation of about 15 feet. So that's not at all bad. We also get our elevation as well. So this system is now worldwide, and it has an enormous number of applications. I call attention to a couple of them here. Aviation, environment, marine, public safety, disaster relief, rail, recreation, roads and highways. I had a friend who was a florist, and whenever they had to make a delivery of flowers and they weren't able to figure out from their maps where the address was, they used to call the fire department, because the fire department knew where everybody was. And it was not a problem. You just called the fire department. They were very happy to tell you. Agriculture, I spoke with a farmer in Indiana a number of years ago who had GPS systems on his plows, seeding equipment, sprayers, and harvesters. And that meant that these things could all operate without drivers. They just take them out to the field, turn on the GPS control, and walk away. So they saved a bunch of money on labor, but they also, turns out, saved money on materials. The amount of fertilizer, the amount of insecticide, etc., was actually lower because the way that the vehicle traveled through the fields was much more accurate. And of course, the police are using GPS because if they get a 911 call from a cell phone, they can pinpoint that. And even if the cell phone caller is cut off or some other reason doesn't get accurate information, they can find exactly where that phone call came from. So I think that the thing that I want to point out is that throughout all of this, the key
No. While we wait for Tim to come back in, I see Terry Jones has joined. Terry?
Yes, I have joined. Sorry for the delay. I just got sidetracked in a number of other little projects I had going today. What did I miss?
A beautiful book review.
Yes.
Oh, yes.
Announced that our next meeting would be Tuesday, July 27th.
Okay.
If you could confirm that
Well,
with the church.
one suggestion I had, if was that a conflict for Tim, or I had heard from you or somebody that every Tuesday was a conflict for Tim Orr.
I heard that from Tim.
What I was going to suggest, and I'm sorry I didn't do it today, was to call the church. And if there's this other group meeting, small group, AA or whoever they are, it seems like in the past they were meeting upstairs in that second floor, small little conference room where we've had to meet a couple of times when they were having their rummage sale. So I was going to propose that we still keep our Mondays and they meet upstairs, but I didn't get a chance to call him today.
Well, if you could do that, and I think we'll go ahead and do Tuesday for
This month, for July.
July.
Yeah.
But could you tell us what you find out?
Yes, I
Because that
will.
would take away a great amount of concern if we could move back to Mondays.
Yes. Okay.
Okay, good.
I will do that.
Thank you. Twice, I believe we've had problems with Tim dropping out of the meeting during his presentation, and he was about ready to share the secret of GPS, I think.
Well, while we're waiting on him, I had a joke 20, 30 years ago before we had cell phones and all the new technology. Did you hear about the drunk who found a payphone and called the operator? And he said, "Operator, can you trace this call so I can find where in the hell I'm at?"
You know, going back to the discussion of the meeting time, I agree with the concern losing Tim Orr at our meeting if we have to switch to the fourth Tuesday. And I'm wondering if there's another central location, a church, a school, a place of business that we might pursue as an option as well if we can't find a way to continue to meet at St. Michael's. Tim is pretty valuable to our meetings.
I agree.
And Terry is going to have a conversation with the church.
Yeah, I'll call him tomorrow and find out so we can get that resolved. There is another church in my neighborhood near Holly in Florida that would be about 10 blocks due east of our old current church location. And the Denver Coin Club meets there on the last Thursday of every month. So I know they allow groups like ours to meet there, and they might be open to a Monday night meeting, and it's a large room with a small kitchen. Not quite as good a lighting as we have at the other at St. Mike's Church, but ample parking. The Denver Coin Club pays them $100 each meeting, and we're getting by at the current rate of $40 per meeting. So that might be a backup too on a Monday.
An expensive backup,
Yes.
unfortunately.
Right.
Do others of us have any locations that we know about or could pursue? And maybe we could take inventory.
Yeah. Well, if Terry's going to have a phone call imminently, that could remove the item from a concern. I don't see Tim coming back, unfortunately.
I found the presentation really fascinating. I've had a GPS for a long time. It's fun to hear how it really works.
Yeah, that's true.
And of course, at its heart,
Shows all the satellites that it's connected to. I had no idea why it mattered. But it's interesting.
well, of course, at its heart is a clock.
Actually, the LORAN that he was talking about was much more accurate during the Vietnam War than people think. We were dropping sensors into Laos within 4 feet of a coordinate point with good reliability during the Vietnam War, and then listening to them with a C-130 flying overhead and using it to vector in gunships on moving trucks. And I've heard the tapes. The sensors were close enough to the trail that you could hear the trucks driving by and the sound of the cannon shells coming down on the trucks. So we could put our sensors pretty damn close to the road with that thing.
I imagine it's the same technology or quite similar with drones.
Well, drone has its own inertial nav plus GPS plus probably some form of TACAN or LORAN as well. So it's got lots of backup.
Yeah.
On a related note, we do have a member. I met him at the Southern Ohio Regional here a couple weeks ago, and I think he's giving a talk next year on a chronometer, a pocket chronometer that he has that has an interesting history. But I understood that he actually worked on the development team for the first GPS receiver that was made here in the U.S. I apologize, I can't remember his name.
Oh.
Going back to the church situation, I may have another place where you could have a meeting, but I don't know yet. So I'd have to ask them.
Okay. Well, and Terry's left the meeting as well, but if we'll hear from Terry, and if we need to go to alternate, sounds like Terry has one that's likely receptive, increase in our monthly costs.
Mine might not be that expensive. It's a different church.
It would be good to have internet connection as well as a criteria so we can continue to broadcast our meetings.
I think they have that.
Yeah. Oh, no, Terry is there. Sorry. Could you, Terry, make that part of your inquiry?
About internet?
Is internet available?
Yeah, I can do that. I know that St. Mike's Church does have it, and we've used it before, you know, when we used to have programs on the, with the National on their video
Mhm.
presentations, and I don't know about this other church.
Well, good.
Does Tim know that he's off? How would we contact him to let him know?
I think it'd be pretty obvious if he starts asking for responses. But it would be good if we could call him, I guess.
Call him or send him an email.
I'm calling him now.
Your call has been forwarded to an automated voice messaging system. 7-2.
Well, David, what's the protocol? Do we,
I just sent an email as well. He's probably got 2 or 3 now. Maybe we wait another 2 minutes, and in the meantime, you can prepare the close of the meeting.
all right. Let's see. I didn't prepare anything, but is there anything else that we should bring up before we adjourn?
Has Dave Fornoff left? I think he has.
Yes.
I was curious about RV parking at Boulder Fairgrounds, just if it gets very busy or what the availability might be. I'll find that out, but I think I just might park my RV there and be there for the duration. I'm looking forward to it. It's been so long since we've had a regional.
Good. Nothing from Tim?
Does anyone know how Ken Rundell is doing?
I talked to him, I think it was Monday, and he's improving, steadily improving. He's doing some work. He had an approximation of the area of bruise, more than a square foot of bruise that had worked its way from deeper in his tissue. And he didn't think he would log in this evening because he's very tired this time of day as his body heals.
I checked in with him this afternoon, and he sent me this message. I'll read if you'd like to hear. Hi, David. I tire by 7 p.m. Sometimes it's all I can do to get that far. Probably I will not call in, but I'll play it by ear. We should check in around 2 weeks from now. I'm improving. I have most of my range of motion back in the shoulder. Thanks. Bruising and road rash diminishing. That was his email today at 1 o'clock.
Ah, oh, very good. That's more current than mine. And of course, the dog is doing well.
Was it an accident or what?
Yes, he was cycling on a trail, not on the road, and someone was walking their dog, and the dog got in front of it. And as you remember from the last time you rode a bike, you know, it's over in a second. You don't even have time to react when you or abruptly thrown off balance. There's only one way it's going to come out, and that's with you on the ground. And the dog probably just wandered off. The owner wasn't particularly helpful, I guess, but they did call the emergency vehicles for him. Yeah. Okay. Well, at the risk of being rude to our presenter, it's been more than 5 minutes since we lost him. And
You need another motion.
David has control. He can end the meeting.
Well, I would suggest we close the meeting, unfortunately. And I'll send our regards to Tim and tell him that we came to adjournment.
I second it.
All right. Well, thanks, everybody. Look forward to seeing you the 4th Tuesday in July. Unless you're not feeling well, in which case, please. Yeah. All right.
Dick. Thank you, Dick.
All right. Good night, all.
Thank you, everybody.
Night.
Good night.